have been discussing application of principles of random vibration to problems in earthquake engineering. We will continue with discussion on applications. So, in this lecture I will consider two more applications. One is in the area of models for accumulated fatigue damage in randomly vibrating structures, and the second one is in the area of vibration energy flow, that is important in the area of high frequency vibrations of engineering structures. So, what I intend to do is to give a flavor of these two application areas and illustrate how principles of random vibration analysis are employed here. The objective is not to describe the problems of fatigue damage nor the problems of energy flow, but to simply state the basic problem and illustrate how random vibration principles could be used. So, we will start with problem of fatigue damage accumulation. So, we will start with some empirical background. What is fatigue? So, we can say that fatigue is loss of mechanical integrity of the structure due to reversal of stresses. So, any structural material on some scale, on any scale, even on very fine scales, will have some imperfections, defects. Consequently, the strength of the structural material in a given volume depends on amount of defect that are present. Now, when the material is subjected to vibratory loads, there will be reversal of stresses, and as a consequence of this the defects and imperfections grow within a given volume of structural material, and consequently the strength of the material reduces, and this phenomena is what is known as fatigue. So, fatigue is essentially a phenomena involving progressive fracture. So, it is a fracture of a structural member due to repeated cycles of load. Fatigue is the primary mode of failure for metals subjected to oscillatory loads. So, this is a major source of failures in aircrafts, railway vehicles, ships, bridges and rotors. Actually, structural components that can carry high constant amplitude loads fail under substantially lower magnitude fluctuating load. This is basically due to fatigue, and during fatigue failure maximum stress could be well below the tensile strength of the material, but the structure fails after oscillating for a finite number of cycles. That is, at failure the response level could be well below the limits of first passage failure. So, its failure could be quite catastrophic. So, it is important to obtain a rational description of how to model these failures. So, the objective of this discussion is to obtain a probabilistic description of fatigue damage in structures which are driven by random excitation. For example, the types of questions that we would like to ask are what is the expected rate at which fatigue damage accumulates, what is the probability distribution of the life of the structure, what is the influence of randomness in structural properties, how to characterize the reliability of structure against fatigue failure. So, we will consider some of these questions and see how we can progress. Now, if you look at time histories of stresses, there are various possibilities exist. For example, in this first one there is an oscillatory load about a mean level, that would mean the load cycle, the stress cycles are completely reversed, and these are called completely reversed cyclic stresses. This oscillation could occur about a non-zero mean. So, the cycling occurs about a non-zero mean which is not 0, or it could be such that there is no stress reversal, but actually there is a, for instance, released tension. Here the stress never enters the compression zone, it remains tensile, but the tensile stress magnitude keeps oscillating. Now, here we introduce certain terms S max, S mean and S mean are the maximum, minimum and arithmetic mean of the stresses. Delta S is the stress range, S max minus S mean, and the alternating stress amplitude is given by delta S divided by 2. The stress amplitude need not be harmonic, the amplitude could vary. For example, here there is a stress time history where up to say 1.5 second there is one amplitude, and beyond that the amplitude increases. Now, the change in amplitude could also be accompanied by change in the mean levels about which these oscillations occur. These are varying amplitude, varying mean stresses, or the stress could be randomly varying in time. It could be multi-frequency. Here what we have shown is a narrow band random process. Here there is no the definition of a cycle here is not immediately evident unless we clarify what exactly that is. Just to illustrate, here I am showing certain measured time histories. For example, in this graph we are showing the time history of the strain on a steel girder bridge as a train formation crosses the bridge at a particular velocity. So, this is second graph is similar result when a longer formation, maybe freight traffic, crosses the bridge. So, the cycle that we see here typically corresponds to the passage of one locomotive and carriage wagon, and these wagon themselves will have multiple axles, and these small oscillations about a higher level represent oscillations due to passage of axles of the same wagon. Now, we use what is known as SN curves to characterize fatigue failure. This SN curve essentially is a plot of cyclic stress level versus number of cycles to failure. That means, if you take a test coupon and subject it to cyclic load at a given stress value, after a certain number of cycles of oscillation, this coupon will fail, and the number of oscillations as a function of stress level is known as a SN curve. So, this is something that is experimentally obtained. This is also known as Wöhler curve. The test specimen is typically a cylindrical specimen subject to uniaxial cyclic stress or a small cantilever beam under bending oscillation. The stress amplitudes are kept constant. We could also simulate actual live stress cycles in a fatigue test, but we can this is not what we are discussing in this lecture. A simple model for the so called SN curves is of this form: ns to the power of b is equal to c, where b and c are constants, and if you take logarithm of this, we get log n plus b log s is equal to log c. That would mean on log scale the SN curve is a straight line with a slope minus 1 by b and an intercept log c. Now, in reality what happens is below a particular stress level there will not be failure due to cyclic oscillations is not possible, and this limit of stress is known as endurance limit, and we are considering stress levels above the endurance limit in our studies. So, number of cycles from this formula ns to the power of b equal to c, we can for this case it is ns to c into s to the power of minus b for s greater than s naught is 0 for s less than or equal to s naught, if you take into account the effect of endurance limit. Now, in the SN curve approach, it is an empirical approach which actually does not deal with the physical phenomena that would be taking place within the material, which results in loss of mechanical integrity. Actually, it does not separate the crack initiation and crack propagation stages, considers only the total life to fracture. Now, we obtain SN curves in the laboratory conditions, and then we want to extrapolate this information to the field conditions. So, laboratory testing is done on coupons, just like with the way we find Young's modulus of a say material using coupons. In the same sense, the SN curves are also obtained in laboratory conditions on test coupons, but these results need to be extrapolated to the field condition. When we do that, there are factors like non-zero mean stress, then varying stress amplitudes, and environmental conditions like temperature, humidity, corrosive media, etc., will start influencing the results, and also the size, shape and surface finish of the member under consideration also have significant influence on the fatigue performance. The frequency of cycling could also be important, but many times this is not a very crucial factor. In the experimental data, actually large scatter is observed. This reflects the influence of uncertainties, and one actually plots, for example, the SN curve. One gets if in an experiment there were a clean straight line won't emerge. So, at any given point you can draw a probability distribution curve, a density function, and one can specify the SN curves in terms of SN and probability curves. This density function could be modeled as log normal or Weibull. Endurance limit I have already explained is the stress level below which the specimen seems to last indefinitely. Now, we use what is known as Palmgren-Minor rule to find out accumulation of fatigue damage. Suppose during the life of the structure, on x axis I am plotting time and on y axis we are plotting stress amplitudes. Suppose the structure undergoes N1 oscillations at stress level S1 and N2 oscillations at stress level S2 and N3 at Ni Ni at stress level Si and Nn at stress level Sn. Now, if the specimen is left to oscillate at stress level S1, it will require say capital N1 number of cycles for failure. Similarly, if the specimen is left to oscillate only at S2, it may require N2 number of cycles to failure, and these capital N1 and capital N2 etc. are obtained from the Sn curve. Now, according to Palmgren-Minor hypothesis, what we do is we find out the number of cycles at different stress levels. S1 is N1, S2 is N2, S3 is N3 and so on and so forth. And for this stress level from Sn curve we get the number of cycles to failure. We define an incremental damage as the ratio N1 by capital N1. Similarly, incremental damage at stress level S2 is N2 by capital N2 and so on and so forth. We define what is known as cumulative damage as the sum of these incremental damage at any given stage. For example, at the end of application of S2, stress level S2 for N2 number of cycles, the accumulated damage would be N1 by capital N1 plus N2 by capital N2. Now, according to the Palmgren-Minor hypothesis, at the end of mth cycle of oscillation, we get the accumulated damage as capital delta is summation I equal to 1 Ni by capital Ni. Now, if I use the formula for the Sn curve, I can write this as Ni Si to the power of B by C, because capital Ni is related to Si and the constant B and C. According to a Palmgren-Minor hypothesis, the condition for failure is that this cumulative damage should reach a value of 1. So, consequently, the safe limit is I equal to 1 to m Ni Si to the power of B divided by C must be less than or equal to 1. If this minor sum crosses 1, the specimen is deemed to have failed according to this theory. A few remarks on the Palmgren-Minor theory could be made. In this theory, the order in which stresses are applied does not matter. That means the damage is assumed to take place in a linear manner. In reality, actually failure is sensitive to order of loading. A high stress level followed by a low stress level would produce accumulated damage of a different kind than the other way around, where a low stress cycle is followed by a high stress cycle. The method as such does not provide any means of assessing the effect of variability in constant B and C etc. And damage is assumed to accumulate at the same rate at a given stress level without regard to the past history. That means it does not take into account the memory. In actual experiments, the minor sum at which the failure has occurred actually varies over a fairly large range, that is 0.25 to 4 under harmonic loading. But for random time histories where no ordered sequence of high and low amplitudes exist, the minor sum is reasonably good, 0.6 to 1.6. Now, the question is, we are not so much interested in the limitations and scope of Palmgren-Minor hypothesis etc. What we would like to consider is how can we extend the Palmgren-Minor hypothesis to random stress time histories. Now, let us assume that the stress time history is a zero mean narrow band Gaussian random process, and consequently if you consider stress to be a time history, there are no discrete stress levels here. Is there not harmonics of different amplitudes following each other? So, how do we proceed? So, for example, this is a sample of a narrowband time history of a narrowband random process. The notion of cycle is not very evident here. This is a narrowband process, but in a broadband process, as we have already seen, the notion of a cycle becomes much less apparent. Here what we define is a function d of t, we define as integral 0 to t chi of t dt, where chi of t is the rate of accumulation of damage. This is this we write as n of t into s to the power of b of t divided by c, and this is fashioned after the formula for accumulation of damage given by ni si to the power of b divided by c. Now, the question is if s of t is a, as I said, zero mean narrowband stationary Gaussian random process, how do we interpret these quantities? If the stress time history is a random process, how do we interpret s of t, n of t in this expression? So, what we do is we take s of t to be the peak magnitude and n of t to be the rate of peaks, and these we have studied already. For a narrowband process, rate of peaks is same as rate of zero crossings for narrowband processes. That means, every time a 0 is crossed, there will be a peak, as you see here. For example, if there is 0 crossing, there is a peak. So, that is a property of a narrowband process. That is not true for wideband process, but we will, to start with, we will limit our discussion to narrowband process. Now, our objective is to characterize the function d of capital T. We are interested in knowing, for example, what is probability that d of capital T is less than or equal to 1. That is a question that we would like to answer. Now, the joint density function of S and N is actually not available. So, what we actually know? We know that peak magnitudes are Rayleigh distributed for narrowband processes, and the expected value of N is given by sigma 2 divided by 2 pi into sigma 1, where sigma 2 is the standard deviation of the derivative of the process and sigma 1 is the standard deviation of the parent process. Now, we make an ad hoc assumption that S and N are independent. So, we assume that the joint density function Psn S comma n is product of the marginal density functions. So, based on that, we find the expected value of chi of t, which is the rate at which the damage is accumulating, and since we know this expression and we know this probability density function, we can write for this expected value this formula. This is Rayleigh density function. So, consequently, this will be the expected value of s to the power of b, and this is this quantity is the actual expected value of n of t, which is again known from study of level crossings and zero crossings of random processes. Now, we recall that the integrals of this type 0 to infinity y to the power of 2 nu minus 1 exponential minus y square dy is actually given by the gamma function. Now, consequently, we can express the expected value of chi of t in terms of the gamma function, and this is what we get. So, at least we are able to proceed and get the with certain ad hoc assumptions the average rate at which fatigue damage is accumulating in terms of the standard deviation of the parent process, standard deviation of the derivative process and the material constants C and B. Now, we can return to the problem of finding expected value of d of t. Now, if process is stationary, we see that sigma 2 and sigma 1 are independent of time. So, they can be pulled out and this 0 to t dt will become this. So, we have this expression for d of t, that is average of the accumulated damage at time instant capital T. Now, we could visualize a t star such that this expected value of d of t becomes 1. Now, if we do that, that t star will be 1 by expected value of chi of t. So, to a first approximation, we can take t star to be the mean fatigue life. So, if you know the random stress time history and you know its power spectral density, you can derive the variance of the process and its derivative process, and if you use this formulary, you have a handle now that you can at least, you are at least in a position to evaluate the mean fatigue life. Okay. This is for a stationary narrow band Gaussian random process. Now a few remarks are in order. In this particular derivation we have taken the constant B and C to be deterministic, but if you happen to know the joint probability density function of B and C, we could incorporate that into the analysis. So the expectation that we have got can be interpreted as a conditional expectation, and the unconditional mean can be evaluated by an integration with respect to the conditional probability density function, the joint probability density function of B and C. It is worth considering the question, is T star indeed the expected fatigue life? Now this needs to be considered carefully. So for that purpose we will consider capital L to be the lifetime. Lifetime is a random variable. So condition for failure, that is the definition of capital L, is 0 to L chi of t dt is 1. That means the expected value of this integral 0 to L chi of t dt is 1. Now this is a condition that we actually need to analyze, but what we have done is we have replaced this integration. The random quantities in this expression is L as well as chi of t, and they are mutually dependent. This integral obviously is not equal to this. This is 0 to mean of L, then mean of the integrand dt is not actually the condition that we are looking for, although this is what we seem to have utilized. So the conclusion is T star is not the exact expected fatigue life, but to a first approximation we could take it as an an acceptable estimate. And if you want to really evaluate this integral in exactly, this is we do not have adequate information on the uncertainties here, therefore we will not be able to proceed anyway. Now we have derived now the expression for expected value of chi of t. With little effort we can also derive the variance of chi of t, and we can also derive the variance of capital D of t. And we have based our assumption on the fact that we are assuming that the stress time history is a narrow band process. If the process is broad banded, then the notion of a cycle and amplitude becomes less apparent, as I already said, but there are algorithms for counting cycles, and some of the algorithms are range pair counting, rain flow counting, etc. They are available, and one could also deal with broadband time histories. So what I have done in this brief presentation is to illustrate how properties of level crossing and peak distribution, etc. could be utilized to get a theoretical estimate of average the expected life due to when failure is defined with respect to fatigue. Okay, now we will move on to another application. This is analysis of vibration in high frequency regime and how we can use random aberration principles for this. Now what is high frequency vibration? We consider that a structure is vibrating in the high frequency regime if its response at any frequency consists of significant contributions from a large number of modes. Now what are the basic problems in such basic difficulties in such problems? For purpose of illustration, I have shown here the transfer function of a frequency response function of a thin walled stiffened cylindrical shell, and as you can see here there are several peaks which are closely spaced. We know that in frequency response functions peaks occur wherever there is a natural frequency, and their variation is also governed by the value of mode shapes at point of driving and point of measurement. So if we consider segments like this, it is very clear that there are large number of natural frequencies that are crowded in this frequency range. So if you were to drive the system harmonically at a single frequency, it is expected that to compute the response we need to consider contributions from several neighboring modes. In that sense we call this type of oscillations as high frequency oscillations. This is not true, for example, in the case of say earthquake response of tall buildings, but whereas in the acoustic response of missile shells or aircraft wings etc., there will be large number of natural frequencies or in the frequency range that we are interested in. I will clarify the nature of the problem as we go along. Now, there is one approach to study such high frequency vibration, and that is known as energy flow models, and one of the techniques or one of the methodology there is what is known as statistical energy analysis, a framework for analyzing high frequency vibration analysis. Now, the structural behavior at high frequencies is very sensitive to minor changes in structural parameters and details of modeling. A deterministic approach to modeling structural system parameters is inappropriate. That means, if a structure is undergoing high frequency oscillations, a slight change in say boundary conditions or some of the parameters of the problem will dramatically alter the behavior of the structure. So, the essence here is that we need to consider this extreme sensitivity of the response with respect to changes in system parameters. Description of dynamic behavior of structural joints with increasing frequencies become difficult. This calls for experimental approaches to characterize structural behavior of joints. So, in a typical structure like automobile vehicle or aircraft structure, there will be several joints, line joints, point joints, etc., and their behavior at high frequencies becomes quite complicated, and if you use methods like finite element method, modeling the flexibility of the joints becomes a very complicated issue as you go higher up in the frequencies. So, the statistical energy analysis procedures essentially take into account these difficult issues. First thing it does is it treats the vibrating system as being randomly parametered. That means, the natural frequencies and mode shapes of the structure is treated as being random in nature. The word statistical in statistical energy analysis refers to uncertainties in specifying the system parameters. The excitations could be random or could be deterministic. So, the stochastic nature in these problems originate due to randomness in system properties. In such problems, detailed characterization of structural response in terms of spatio-temporal variations of displacement, stress and strain fields becomes unwieldy. Macro level description that involves space, time, frequency, average response quantities such as vibration energy content in spatial domains within a structure may be adequate. So, the method of analysis is aimed at establishing spatial distribution of vibration energy stored in the structure as a function of frequency. So, I will just illustrate what that means, what I said. Consider a simple truss here which is carrying a force f of t. Let us assume that the frequency range of f of t spans several decades of frequencies. It may go up to a few tens of hertz to a couple of thousands of hertz. We could use finite element method to analyze this problem, but then if we need to compute the natural frequencies of this structure over a frequency range of say 2 kilohertz, there could be several maybe hundreds or couple of hundreds of natural frequencies which could lie in that frequency range. Now, if we indeed perform, that would mean that we need to model this structure in greater detail. We need to select elements which are quite small in size. We should have a large number of such elements. That in turn requires that we should be able to know the property of the structure at smaller levels, smaller spatial levels, and that may not be always possible. Similarly, the question on how does this joint behave as the frequency increases becomes crucial. So, any slight change in system parameters here can dramatically alter the behavior of the system. So, therefore, if we are interested in, for example, displacement, stress or strain at any given point in the structure, we end up doing huge amount of calculation. But that type of information may not be needed to take decisions in this type of problems. What we may like to know is what is the total energy that resides in this member. what is the total energy that resides in this member, or how does the total energy gets spatially distributed in the system. For that purpose what we do is we divide this truss into a set of subsystems, each one is an energy carrying unit, and we would like to now consider the problem of this force into the velocity. Here will be the power input to the system. That power should be stored at various points in the structure, and they which are the more energetic members, and if that level of energy is high, how do I reduce it, what are the vibration paths that take this energy to different parts in the structure. So, this type of questions are asked in statistical energy analysis. So, statistical energy analysis can be viewed as a branch of linear vibration theory with some of the following characteristic features. Here the built up structure is taken to be random in nature. It is divided into a set of subsystems, and the subsystem natural frequencies are taken to be identical and independent random variables distributed uniformly in the frequency range of interest. That would mean the natural frequencies of the subsystems are taken to constitute Poisson points on the frequency axis. That means natural frequencies are number of natural frequencies is a Poisson random variable. The external excitations that are often random in nature are specified in terms of power input, and the governing equation for system behavior are described in terms of power balance between subsystems. We do not write the equilibrium equation the way we do in finite element method, we simply keep track of energy balance. I will come to some details. The primary objective of the response analysis is to determine the spatial distribution of total vibration energy residing in the system. It is not to obtain, for example, time histories of stresses, strains and displacement at every point on the structure. Here it is a macro level description where certain spatial extents are identified as subsystems, and what happens within that spatial extent in terms of a single number is what is being sought. Here are some references. There is a book by Lyon and De Jong, Theory and Application of Statistical Energy Analysis. There is an introductory paper and a review paper which provides some background to this subject. Here is another example where there are a stack of 3 plates. This could be a typical situation in solar panel arrays in satellites. This e raised to I omega t is a forcing function that acts on this, and this frequency can cover several, it could run from 20 to say 2 kilohertz. What we are interested in knowing is under this kind of excitations, how does vibration energy reside in different parts. So, we could model this in terms of subsystems as shown here. 1, 6 and 11 correspond to these 3 plates. This 1, 6 and 7, 1, 6 and 11 correspond to the 3 plates, and 2, 3, 4, 5 and etc. 7, 8, 9, 10 are these coupling members. We are not interested, let me again emphasize, in finding stresses, strains and displacement at various points on the structure. Now, how do we specify inputs in statistical energy analysis? We do not give time history of the force, but we would like to provide the input power. This input power is derivable in terms of the input power spectrum and the input power receptor. That means the force into the velocity, applied force into the velocity in the direction of the force is the power. Force into displacement is the work done, and for that work done per unit time is the input power, and in terms of a spectrum, if you want, you have to do certain calculations. Now, we consider the inputs to be in the high frequency range, say 20 to 20 kilohertz. These excitations could be random or they could be deterministic also. It is not important that the randomness resides in the excitation, the randomness is in the system parameters. How do we model the system? We model the system as collection of energy storing elements called subsystems. They are not like finite element elements, but they are much more macro level description. They involve much macro level description of the system behavior. We focus only on linear and randomly parametered systems. The behavior is linear, but the system is randomly parametered. This randomness in system parameters could be introduced at the level of definition of mass, stiffness and damping. as being random, or alternatively we can directly characterize the natural frequencies and mode shapes of the subsystems as being random. We need not have to specify mass, stiffness and damping as random, but since solution is being obtained in modal domain, the modal parameters like natural frequency, mode shapes, participation factor, modal damping etc. could be taken as random. And what are the response quantities we look for? We look for steady state, time averaged, total energy stored in each subsystem, often averaged over frequency and ensemble of random realization. That means we are looking for grossly averaged features, we are not looking into details. It is average over time, average over space, average over frequency band, and it gives a broad idea about the different levels of energy that stay at that reside at different levels. How do we derive the Gowning equation? What are the Gowning equations in SEA? The Gowning equation in SEA represents condition of power balance, and it has a form: the vector of power input is equal to a matrix multiplied by energy at different energy residing in different subsystems. This matrix is known as coupling loss factor matrix. I will talk about this shortly. This is essentially a representation in the steady state. We do not normally consider transient behavior using SEA, and the whole analysis is done in frequency domain. Now we can ask, are there any theoretical foundations for this procedure? Actually there is no such rigorous theoretical foundation. There is no, for example, a variational principle from which we can derive SEA equations, nor there is any systematic proof that as we increase the number of subsystems in SEA formulation the answer would converge. So it is not like a method like a finite element method, but it is a heuristic procedure which is found to work well when other methods do not perform. Now having said that there is no theoretical basis, but there exists an idealized situation where statistical energy analysis, basic results of statistical energy analysis can be shown to hold good. So what is that system? There is a simple system. There are two oscillators which are coupled through a coupling spring. The two oscillators are driven by F1 of t and F2 of t. These are taken to be independent Gaussian white noise processes. Now the question that we would like to answer is, this F1 of t will do some work on this displacement, therefore there will be a power input here and there will be a power input here, and how does vibration energy get shared between this subsystem and this subsystem. So what we do is we model the problem using two subsystems. This is one oscillator, this is second oscillator, and there is a coupling Kc, and please note that the coupling element does not have damping. It is a conservative coupling. So what happens? There is a power input to the first system through F1 of t, and part of the power is dissipated through damping, and part of that flows to the energy flows to the second subsystem. And in the second system, because of F2 of t, there is some power input, and part of it is dissipated and part of it flows to subsystem 1. So now we set up the simple equation that pi in 1 is equal to pi 1 2 minus pi 2 1 plus pi dis 1. So pi in 1 must be equal to this. Similarly, what comes into second system? Pi in 2 plus pi 1 2, and what goes out? Pi dis 2 and pi 2 1. So pi in 2 must be equal to pi 2 1 minus pi 1 2 plus pi dis 2. So this is, there is no approximation here, this is exact. Now let us try to evaluate the expressions for these input powers, and maybe we will take expected values and see what happens. So to do that we will write the equation of motion. Now the equation of motion consists, this is simple to derive, the 2 degree approximation, a 2 degree freedom model, it gets coupled through the spring Kc, and this is reasonably straightforward, and we are assuming that F1 of t has 0 mean and it is a white noise with strength I1, and F2 of t also is a white noise with strength I2 and 0 mean, and we assume that they are uncorrelated. That means they are independent because we are assuming Gaussian white noise models. The equation can be recast as in this form, where we are taking the force acting on the first system through the coupler on the right hand side. so we assume that since the system is damped, we assume that as t tends to infinity the system reaches steady state, the input is stationary, system is damped. Now we will digress for a moment. If you consider a single degree freedom system under a white noise excitation, in the steady state, if you want to find out the cross power spectral density function between displacement and the applied force, this can be derived in terms of this well known expression, and the Fourier transform of the response is related to the Fourier transform of the input through the system transfer function, and we get this Sxf of omega to be h of omega into Sf of omega. Since excitation is white noise, I get this as h of omega into S naught. Now what is a cross covariance? It is the Fourier transform of this, so I get this expression. Now at tau equal to 0, I will get Rxf of 0. Rxf of 0 can be obtained by putting tau equal to 0, but you can see that the integrand is nothing but the Fourier transform of the impulse response function. Okay. So Rxf of tau is S naught h of tau by 2 pi. Now in this, if you put tau equal to 0, I get Rxf of 0, which is S naught h of 0 by 2 pi. Now we know by definition h of 0 is 0, therefore Rxf of 0 is 0. So that result I will be using, so that this is a minor digression to make sure that that is registers on your mind. Now we would also need another result. If x of t and y of t are jointly stationary, the expected value of the product of nth derivative and mth derivative of x and y as shown here is given by this. This we have derived when we introduced the basic notions of mean square derivative of random processes. Now we can consider certain expectations. F1 of t into y1 of t is 0, using the logic that I just now described. We can also show that some of these are 0, and since process is stationary, the process and its derivative at the same time are uncorrelated. So again that would mean these expectations are 0, and expected value of y1 into y1 double dot using this formula can be shown to be given by this, and we have several other expectations that we need when we work with these equations, and I leave it as an exercise to verify each of these statements. These are already covered in the lectures, so it is a good time to check your understanding by showing that each one of these statements are true. Now what is it we are interested in? We are interested in the average power input, that is expected value of pi 1 in. What is power input to the first mass? That is applied force F1 of t into dy1 would give the work done, and into dy1 by dt would give the work done per unit time. So pi 1 in expected value is nothing but expected value of F1 into y1 dot. Similarly pi 2 in will be F2 into y2 dot. What is power dissipated? It is C1 y1 dot square. Pi 2 dissipated is this. What is pi 1 2? Pi 1 2 is the force in the spring acting on velocity of this. So that would, you can show that that would be given by Kc into y1 into y2 dot, and pi 2 1 will be Kc y2 into y1 dot. Now if, since y1 of t and y2 dot of t is 0 and it is not 0, it is equal to minus y1 dot y2 t, it follows that pi 1 2 is equal to minus pi 2 1. Now we can recast all these equations in a matrix form. So on the left side I have pi 1 in here, pi 2 in, and all other expected values. I mean I am writing, I mean you have to recast that set of equations in this form. We get this equation. This is a straightforward representation of the equation that we considered just now. Now in this we will now consider some of the rows. Suppose if you consider the first two rows, I get C1 into y1 dot square expected value plus Kc into y1 y2 dot is equal to F1 of t into y1 dot. Similarly C2 y2 dot minus Kc into y2 y1 dot is this. These two equations are nothing but the statement of law of conservation of energy, that is pi 1 dis plus pi 1 2 is pi 1 in, pi 2 dis minus pi 1 2 is pi 2 in. So, things gel well, there is no problem. Now, if we consider rows 5 and 6 in that equation and take a look at this equation, you can show that what they are telling us is the average kinetic energy in the first system minus plus average potential energy in the first system is given by this. Similarly, this for the second system, this is the equation. Now, if for instance, if coupling spring is absent, then we know that in the steady state average kinetic energy is same as average potential energy, and that again is consistent. Okay. Now, if we assume that this coupling spring is much smaller than K1 or K2, that means the coupling is weak. This is one of the assumptions that is made in statistical energy analysis. And if you now consider expected value of y1 into y2 dot, you can derive this expression, and you have to carefully look at this expression. This is expected value of y1 into y2 dot is nothing but expected value of pi 1 2 multiplied by that Kc. We denote this multiplier, see the term inside this bracket is of importance. You can see that this is pi 1 divided by C1 into expected value of pi 1 in, and this is M2 by C2 into pi 2 in, the second term. So, what this is telling is that the energy flow from 1 to 2 is proportional to the difference in energy or difference in the power input between the first and the second system, some scaled factor. Now, we will manipulate this and see what it tells us. Now, again under the assumption of light coupling, we can show that the power input is in steady state is dissipated by the system. So, that is C1 y1 dot square. So, I can write for pi 1 in 2C1 by M1 into KE1. Similarly, expected value of pi 2 in can be given by this expression, and we use the fact that in steady state average kinetic energy and average potential energy for the two systems are equal, and if I now substitute, I get what is known as a fundamental statistical energy analysis result, namely that average energy flow is proportional to the difference between the energy between two subsystems, the energy in the two subsystems. That means, just like thermal energy flows from hot spot to cold spot, the vibration energy also flows from places of high energy concentration to low energy concentration. So, this is the essential fundamental result of SEA, and this is this has basis in random vibration principles. That is what I am trying to discuss. Only that aspect of SEA is what I am discussing. Then we have considered two oscillators. Now, what happens if there are two continuous systems? So, for example, a plate is coupled to a cantilever beam. This plate itself is a multimodal subsystem. It has several natural frequencies. In its uncoupled state, if I were to perform a modal analysis, in the frequency range of interest, there may be several modes. That means, this plate will be represented by a set of single degree freedom systems corresponding to the normal modes, the independent generalized coordinates of this plate. Similarly, the cantilever beam also can be represented as a set of oscillators. Now, that we notionally represent like this. This first picture here is, this is a plate, and these are the oscillators that correspond to the generalized coordinates in the frequency range of interest. Similarly, this is a beam where there are few more oscillators here which correspond to the generalized coordinates of the cantilever beam. This system receives some power pi 1 in, and it dissipates some power pi 1 dis. Similarly, this system receives pi 2 in and dissipates pi 2 in. Now, we have studied how energy exchange takes place between two oscillators. Now, what we do is, we assume that the energy flow from plate to cantilever consists of energy exchange between the oscillators in this set with oscillators in this set. That means, this oscillator exchanges energy with this and this, and similarly this oscillator exchanges energy with all the oscillators here. So, that means all these oscillators exchange energies. Now, the average power flow from alpha to beta, that means plate to the cantilever, is given by the a constant multiplier, which is again dependent on the plate and cantilever characteristics, and in some sense an energy difference between the two plates, that is total energy divided by number of oscillators that are participating. What is the energy density or the concentration of energy is total energy divided by number of oscillators. It is like temperature in thermal analogy, right. So, it is a hot means total energy divided by number of modes is high. So, here total energy divided by number of modes here. So, the flow takes place from hot spot to the cold spot, and that the energy flow is proportional to the energy difference, and this proportionality constant involves the properties of the structure. So, we have omega is the central frequency, delta omega is the frequency bandwidth, and expected E alpha is total average energy in the subsystem alpha, and n alpha is the number of modes per unit frequency interval for the subsystem alpha. That means omega that defines this, that the way the energy is defined, this factor is relevant. So, what this means is energy flow between conservatively coupled linear subsystems excited by broadband random excitation is proportional to the difference between subsystem average modal energies. Now, this proportionality constants etc., this is known as coupling loss matrix, coupling loss factor matrix, the elements of that have to be determined by, in this particular case when we discuss two oscillators, we derived this H12 that is shown here using random vibration principles. Okay. So, the SEA equation, the equation that you will actually solve when you apply statistical energy analysis will be in this form. The unknowns are these energy levels EI and EJ, this is E1 and E2 in this particular two subsystem problem, and the excitations or the inputs is in terms of power, pi in 1, pi in j, this is known. These are unknowns, and this is analogous to our stiffness matrix, but this is known as matrix of coupling loss factors. Typically, these coupling loss factors could be estimated experimentally, where you know the difficulties associated with joint flexibilities and in randomness etc. in the system properties can be taken into account, or analytically using wave propagation concepts. I will not get into that. The same logic if you apply to a set of n subsystems, we get the unknowns are E1, E2, E3, ENS, where NS are the number of subsystems, pi in 1, pi in 2 and pi in NS are the inputs, and this is the matrix of coupling loss factors which has to be determined either experimentally or by analytical, and the principles of random vibration analysis are relevant in this context. So, the subject of statistical energy analysis is quite vast, and I have given you a few suggestions for further reading. There is a review paper by Fahy, Statistical Energy Analysis, a critical review, and there are two papers, one by Langley and another by Keene, which contain quite useful information. Now, with this we will conclude this present lecture. In the next set of 4 lectures, we will consider certain problems which basically would help you to learn the subject. So, the discussion on principles of random vibration analysis and the methods and the basic problems etc. now closes. In the remaining 4 lectures of this course, we will consider a set of problems and tackle them. We will conclude this lecture at this stage.